morning or good afternoon, everyone, and welcome to our first online lesson. Today, we will be talking about algebraic vectors in R2 and R3. Let's take a look at the title and let's try to understand each part of the title. First of all, algebraic vectors. What we have been studying so far, we've been studying geometric vectors. What we are going to do from this point on, we're gonna add the power of algebra to our vectors. So from this point on, we will study algebra of these vectors. So far, so good. Now, what else do I see in my title? Here I see r squared, r cubed. Again, let's go back to our previous knowledge. Whenever I see something to the exponent of 2, the way I feel like writing something like that is r times r. Now, the big problem is that I cannot multiply a set of real number by itself. What is the meaning of r times r? Let's take a look at a Cartesian plane. And let's place a point in this Cartesian plane. A random point, for example, of coordinates 3 and 2. How do I describe this point? Well, I know that the x-coordinate of this point is 3. The y-coordinate of this point is 2. For any coordinate, for any point in the Cartesian plane, the unique way to determine that point is to give the x-coordinate, which is nothing else but a real number. So x-coordinate, which is nothing else but a real number, and the y-coordinate, which is nothing else but a real number. So we have now a pretty good understanding of the meaning of r squared. I am pretty sure that you will guess the meaning of r cubed. It's nothing else but r times r times r, which means I will be talking about ordered pairs x, y, z, where each of these coordinates x, y, or z are real numbers. Good. So now that we got this, let's move on and let's take a look at vectors in R2. Two-dimensional vectors in a Cartesian plane. What I have here on my Cartesian plane, I have some vectors. What do I notice about these vectors? Number one, I notice that they all have the same direction. Yes, they are parallel, they have the same direction. Another thing that I noticed about them is that, we looked at the direction, it makes sense to look at the magnitude. Let's take a look at the magnitude of one of these vectors. For example, this one over here. To create a right angle triangle, I go up 2 units, 3 across, so the magnitude of this vector is 2 squared plus 3 squared, square root of 30. Now, if you go at all those 4 vectors, you will notice that all of them will have the same magnitude, square root of 30. So, same direction, same magnitude. Okay, so same direction, same magnitude. Guess what? My 4 actually vectors are equal vectors. Now, there is one vector that will play a huge importance huge importance for us. And that vector is a vector that starts at the origin, and so the tail of this vector is the origin, and the head is point P of coordinates 3 and 2. Vector OP is called a position vector. Position vector. Don't forget, it's equal to the other one. What is special about this vector is that it starts from the origin. Now, the notation I'm going to use for this vector is OP, and I'm going to define this position vector using the x and y coordinates of point P. So, vector OP is defined at 3, 2. This is the way I will define vectors in 2D. Now, let's go and do the same thing in 3D. I need a new dimension. So I have x-axis, I have y-axis, so I have my old xy plane. From this point on, when we talk in 3D, I want you to think of your desk, the surface of your desk, as the old xy plane. We will be adding a new dimension. We will be adding the z-axis from your desk going straight up. So let's take a look together. This is my x-axis. This is my y-axis. So right now I created the plane of your desk. Now perpendicular to your desk, let's create the z-axis going straight up. Another way, you have here the same xyz plane from at an angle. That might help you see a little bit better the positive x, the positive y, positive z. Now, let's try together to represent the vector, a position vector in our cube OP that is given as 2, 4, and 5. What does it mean? It means that the coordinate of point P, the x-coordinate of point P, that will be x. The y-coordinate of point P, that's 4. The z-coordinate of point P, that is 5. Okay, so let's try to do that. I need an x-coordinate. I have here an xyz system of coordinates. Let's try together to place point P. First of all, I need a positive x of 2. 1 and 2. There you go. Then I need a y, a positive y of 4. 1, 2, 3, and 4. There you go. And then a positive z going up of 5. 1, 2, 3, 4, and 5 over there. Good. So now let's do exactly what we used to do in 2D, but this time in 3D to get to point P. So what would I have done in 2D? I would have drawn some horizontal and vertical lines. So I would have done something like that, parallel to y-axis, then something like that, parallel to x-axis, then I'll go up, vertically up, parallel to y, like that, parallel to z, like that, parallel to z again, from 2, like that, Very good. Yeah, we're gonna adjust a little bit in the end. Now a little bit tricky. This is a little bit tricky. Parallel to. Are they quite parallel? Yeah, we can live with them. Horizontal here. And there you go. Good. So, we need a little bit of adjustment here and here. Okay. It's pretty good. We can live with it. Okay, so what did I create? Oops, I don't need that. Let's get rid of it. Good. So I created my point P is right here. My point P is right here. What are the coordinates of point P? 2, 4, and 5. X coordinate 2, Y coordinate 4, Z coordinate 5. Yes, that's exactly what I got. And one more thing I need to create the vector OP, the position vector. How do I create it? I'm gonna join the origin to point P, and this is the position vector OP. Let's make it nice and colorful. What color do we want? We want it blue. Okay, so there you go. That is the position vector OP. Your task right now is to show me a second vector, vector OR, given as -3, 2, 2, -5. There you go. Enjoy, and let's see what you get.